And I would encourage you to study the solutions to these and see what should have been if you didn't get all the points, and that's the case for many of you. So anyway, I'll begin with a word of prayer. So, dear Father, we thank you for this day again. I thank you for these students and this class. I just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. Okay, so today I want to talk to you guys about integral vector fields. Not integral vector fields, integral curves of vector fields. Another word for this would be like flow lines. All right. So what's a flow line to a vector field? So let's try to describe it, and I'll be. I mean, we could either go 2D or 3D. I suppose you could go more, but let's give a definition. Definition. An integral curve to a vector field F, all right, and we'll call the integral is a path, let's say phi, I guess I'll use r, that goes from some interval of the real numbers to, let's say, Rn, and dr dt is equal to f of r of t for each t in the domain of definition here. So, just let me foolishly attempt a picture here. So if you're, a two-dimensional vector field, looked like this, let's say, all right, then an integral curve, if you were to try to plot it, would be something where wherever the curve goes, right, when it touches that, there's one that goes through here like that, roughly speaking, right? Maybe there's one like this. Maybe there's one like this. Something like this, right? These are some integral curves, to the limits of my artistry here on the board and so forth. But a path is a parameterization, right? A parameterized curve, and so it's got a sense of direction. And so the point is, the integral curve is such that its tangent field, right? Its velocity field directly matches the given vector field at each point that you can consider it. All right. Now, we talked about these earlier in the course a little bit, and we did a trick earlier. First of all, we didn't think about it in n dimensions, for sure. And we just looked at it in 2 dimensions, and in 2 dimensions, there was this kind of sneaky trick we could do where we eliminated the time variable by, like, dividing dt's. And so, like, on test 1, I think you had a problem where you found the integral curve. You do, for pq, you do dy dx is equal to q over p, you solve it, right? We talked about this before. But now, we have more to work with, right? So example 1, we could look at finding integral curves of a following vector field. I'll do a 2-dimensional one to get us started here. F of x comma y, the vector field I'll look at will be, say, minus y comma 4x. All right. I want to find the integral curves. Find integral curve, or if you like, find the flow line, or the streamline, if you like, through the point x naught, y naught. We'll do it through an arbitrary point, okay? So that's the problem. And so first order of business is to, like, decide a notation to sort of work through the math, all right? And what I'm going to do is I'm going to use the notation like r equals to xy, right? So if I look at that, my dr dt is then dx dt, dy dt, right? And I want that to be equal to minus y comma 4x, right? And so what are we up against? Well, we're up against a system of differential equations, right? So we're up against dx dt equals to minus y, and dy dt is equal to 4x. Now, last time I came up against this kind of problem at the start of the semester, I just pulled some hocus pocus and solved it through some guessing. But now we have a method. This is a problem that we can solve, right? This is, you know, xy prime equal to what? 0, minus 1, 4, 0, xy, right? So it's a constant coefficient 2 by 2 problem. And, well, we can solve this, all right? It turns out that here, A has eigenvalue lambda equal to plus or minus 2i. And if we use lambda equals to 2i, you get the eigenvector like 1, 2i. And as such, we find the general solution has the form r of t equals to, like, let's see here, c1 times cosine 2t minus the sine of 2t plus c2 times the sine of 2t and 2 cosine 2t. All right. Now you can look at where am I getting this from? This is example 4.46 in the notes. All right. All right. So you can, all of the details are right there in terms of like the eigenvectors and all that. All right. And so what I did was I just, you know, these are the real and the imaginary parts of the, you know, the complex. Oh, I missed a 2 here. There's a 2 here as well. 2. All right. So that's the general solution. But I don't want just the general solution. What do I want?
The flow lines.
I want the flow line through that given point, right? X naught, Y naught. So how do I figure that out? Well, so, like, let us understand that we want this, we desire this, you know, this at what, at time what? Let's make it time 0, right? Time 0 seems nice. And that's kind of like the standard thing. If somebody asks you to find a solution through a point, everything else being equal, try to make it happen at time 0, you know, if you can. All right, so what do we got? So R of 0 is what? It's apparently C1 times 1 minus 2, right? Plus C2 times 1, 2. Now, why is that wrong? I did it wrong on purpose, okay? 2 of those are wrong. What is sine of 0? 0, yes. I like the disappointment with which you said 0. That was very good. That's the kind of... that's the kind of, dismissive, that was the right tone for that comment. Right? So 2c2, now this is equal to x naught y naught, right? And so apparently the integral curve that we're looking for here is simply r of t is equal to, I can write it all out as one big old thing, x naught cosine 2t, and down here minus 2x naught sine of 2t, because c1 apparently is equal to x naught, right? And then y naught, c2 is what? Y naught over 2, right? So plus y naught over 2 sine of 2t. And then this be canceled, so plus y naught cosine of 2t, right? And there you go. That, my friends, is the integral curve. And you can check your answer, right? If I plug in times 0, what should we get? We better get back out x naught y naught, right? And that's what we get because the sign is 0 at 0. So it just leaves us as x naught times 1 and y naught times 1, and there it is. Now, what did we do before? How did we solve this problem before? We didn't solve this problem this way before, right? When I asked you to find the integral curve before, I asked you to do it in terms of Cartesians, right? And so there we were using a trick that was, basically saying, okay, so if we want, dr dt, I'll go back to the PQ notation for a second here, guys, right? So if we want that, we've got dx dt, dy dt, right? And what we said before is, okay, so that means that we want dx dt is equal to p and dy dt is equal to q, right? And so what I did was I said, well, check that out then. dy dx we can look at as dy dt over dx dt if we think about the connection between a parametrized curve and its corresponding Cartesian equivalent. But dy dt was q and dx dt was p, so lo and behold, if we were just interested in the Cartesian equation, we can solve dy dx equals to q over p. Now here q was 4x and p was minus y, right? So we separate variables. You got yourself minus y dy plus, let me write it this way. We've got, y dy plus 4x dx is equal to 0, right? Actually, forget about separation of variables here. I'm just going to do exact equations. Because if you look at that, you can easily go, this is just the differential of what? Bless you. What's that? No? How about 1/2 y squared? Yeah? Plus what? How can I get a 4x dx from the total differential? 2x squared, right. 1/2 y squared plus 2x squared. That is equal to 0. And that then immediately tells me, by calculus, that 2x squared plus y squared over 2 equals to a constant. This is the Cartesian description of the integral curve, right? Now, if you want to make it go through x naught, y naught, what would you do? 2x squared plus y squared over 2 equals to, I don't know, how about 2x naught squared plus y naught squared over 2, right? So there you go. That is the Cartesian equation of the integral curve through x naught, y naught, which makes it relatively evident what the nature of the curve is, which is what? Circle is kind of right, but an ellipse, yeah. So a squished circle, but yeah, there it is. An ovally. I'll allow it. All right, so integral curves in the plane, we've got two choices, right? We can either, we can find the Cartesian form of the integral curve, or better yet, we can find the path which parameterizes the integral curve. What's in black is a little bit better because it actually points in the direction of the vector field, right? What I put in blue doesn't capture the direction at all, right? We'd get the same integral curves if you replace PQ with minus P minus Q, same quotient, same separation of variables like the XY problem. So there's more information in the parameterized integral curve, the flow line. I mean, flow lines have a direction, right? Okay, so let's do another one. Example 2. I'll do a 3-dimensional one for you guys. If I can find one. Trying to find one that's got the full solution. Yeah, okay, this one's okay. So here is one. Example 2. Suppose we want to find the flow lines, find integral curves of f equal to, let's say, all right, I got to think here. Y, z, x minus y plus z. All right, so this is based on example 4.4.14, where we learn that if you look at dr dt equal to 0, 1, 0, 0, 0, 1, 1 minus 1, 1 times x, y, z, well, we learn how to solve that, right? But that is exactly the system that you're trying to solve for the integral curve here, right? Like, we have dx dt equals to, what is it, y? dy dt equals to, what is it, z? And what's the other one? I can't see. dy dt equals to z, and dz dt equals to, well, that, right? All right. So, this means that we need dx dt equals to y, dy dt equals to z, and dz dt equals to x minus y plus z. And that is exactly, right, is exactly that problem. All right? And the solution to that is given in the notes. And the solution is r of t equals to c1 e to the t times 1, 1, 1 plus c2 cos t minus sine t minus cos t plus c3 times sine t cos t minus sine t. So you guys tell me, what's the details of the problem here? What happened? What were the eigenvalues for this matrix? If you want to read it backwards, can you reverse engineer this?
0 and 1 will just be, well,
Plus or minus I.
Yeah, okay, yeah, this tells me eigenvalue 1. Good, good. And this tells me, these guys tell me what? Eigenvalue what? I, yeah, plus or minus I, right? Okay. And I mean, apparently the eigenvector, right, with the complex eigenvector would have been, it was Oh, no, I'm not going to try to do that. Whatever. Who cares? You can figure it out. That'd take me a couple minutes. It's not interesting. Let me not do that. But I wanted to go through, I wanted this to go through the point what? I went through x naught, y naught, z naught, all right? At time 0. So we plug in time 0, and that gives us x naught, y naught, 0, x naught, y naught, z naught, equal to what? Well, C1, C2, C3, right? Good grief. I meant C1, 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 right? I'll tell you what, I'll keep the C1 out front. This is C1 times 1, 1, 1, plus C2 times what? 1, 0, minus 1, plus C3 times 0, 1, 0. So, like it or not, we've got to solve 3 equations and 3 unknowns, right? Fortunately, we all know how to do that because it's high school math. And high school is definitely a prerequisite for university, I think. I mean, I'm a high school dropout, but whatever. I got my GED, though it counts. True story. Anyway, all right, so maybe this is a good time for us to take a second to talk about how to solve this system. I mean, we've got 1, 1, 1, 1, 0, minus 1, 0, 1, 0, right? Times C1, C2, C3 equal to x naught, y naught, z naught, all right? And probably the most reliable way to solve this kind of problem is by something called row reduction, which I haven't taught in here, you know. And the reason I haven't taught row reduction in here is because we haven't needed it. Because all the eigenvector problems that we've come across in class have been simple enough that doing row reduction would do violence to the algebra. It was just easier to just solve them directly. But this, I think row reduction is not a bad idea. So let's talk about row reduction. 1, 1, 0, 1, 0, 1, 1, minus 1, 0. And we put the inhomogeneous terms over here. All right. So the way row reduction works is you're allowed to do row operations, and you try to play this game where you clear out the numbers under the pivot position. So to start with, I make my upper corner the pivot position. I want to clear out the ones below it. So to do that, to achieve that goal, we do row 2 minus row 1, and we do row 3 minus row 1. So when that happens, nothing happens to row 1. Row 1 stays just as it is, 1, 1, 0, x naught. All right? So what we're doing right now is called the auxiliary coefficient matrix. It's a simple notation for writing down a system of equations without writing the variables. All right, so as I subtract the coefficients from row 1 and row 2, 1 minus 1 is 0, 0 minus 1 is minus 1, 1 minus 0 is 1. Row 3 minus row 1, 1 minus 1 is 0. Minus 1 is minus 2. And 0 minus 0 is still 0. All right, so row 2 minus row 1 was the last column. I get a y naught minus x naught. And I get a z naught minus x naught. At this point, we're done with pivot position 1. And we can go on to pivot position 2. Now, the standard algorithm says you clear the things out below the pivot positions and you do something called the forward pass. And then once that's done, you go back and do the backwards pass. But there really is nothing written in stone that you have to do that. This one right here, I'm just going to destroy above and below the pivot position all at once, since I can. And so what I'm going to do is my next move, I'm going to do row 1 plus row 2 for that. And down here, I'm going to do row 3 minus 2 row 2 for that one. All right, so row 2 is unaltered. 0, minus 1, 1, y naught, minus x naught, all right? Row 1 plus row 2. All right, so I got a 1. I hope I got a 0, all right? And I got a 1. 1 plus 0, 0. And when I add row 1 to row 2, the x naughts be canceling. I'm back to y naught again. All right, row 3 here, 0. I sure hope that's 0. I think we get a minus 2, all right? And then row 3, which was z naught minus x naught, minus twice the row 2 entry, which was y naught minus x naught. So how does that simplify? Does it simplify?
Wait, why is the top term y naught instead of y naught plus x naught?
Well, it's y naught, this y naught was x naught plus parentheses y naught minus x naught.
Gotcha.
So I'm taking the third component here, right, this guy, right?
Yeah.
And now I'm subtracting twice of that. So I think if you look at this, this gives us a minus x naught plus 2x naught, so that's x naught, right? So we have x naught minus 2y naught plus z naught, I think. That's how that simplifies. All right. All right, so one more move. So we have now, all right, so, rats. Fine, I'm this far in, I gotta finish it. So we've got 1, 0, 1. 1, 0, 1, y naught. 0 minus 1, 0 minus 1, 1, y naught minus x naught. And the last one I'm going to divide by minus, I'll just divide by 2, how about that? 0, 0, minus 1, I'm dividing by 2. Row 3 divided by 2. So I get 1/2 of x naught minus 2y naught plus z naught, if I haven't made a stupid mistake at this point. All right. So finally, we have reached the third pivot position right here. And to get rid of these guys, which is what I'd like to do, I will simply do row 1 plus row 3, and also row 2 plus row 3. All right. And so we get 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1, which is lovely. Now, nothing happened to row 3, so that's still 1/2 of x naught minus 2y naught plus z naught. All right. And row 1 plus row 3, like maybe it's helpful to also write this as 1/2 x naught minus y naught plus 1/2 z naught, yeah? If we look at it like that, it's kind of helpful as we add it to row 1, because then you can see the y naughts just are canceling and you've got 1/2 x naught plus z naught. And row 2 plus row 3, again, the y naughts be canceling, and we just get like minus 1/2 x naught plus 1/2 z naught. All right, so what this tells me is, first of all, C1 is equal to x naught plus z naught over 2. This tells me that C2, notice that there's a minus 1 here. So to get rid of that, move it to, so anyway, that minus I'm counting for in this solution, so that gives me x naught minus z naught over 2. And this one gives me that C3 is 1/2 of like 2y naught minus x naught minus z naught. Write it however you like. All right, so coming back to the start, we have r of t is equal to, my C1 was what? 1/2 x naught plus z naught. And that gets multiplied by e to the t. My C2 was, what was it? X naught minus z naught over 2. Now there I got to be careful. C2 picks up what's cosines and sines. So we got to put them as appropriate from the general solution, all right? So I've got, let's see, the top one's got I got cosine. So I've got a cosine t. I'm going to throw the minus over here, guys. So minus, there's a sine t. And then throw that minus over here, minus cosine t. All right. And then the unpleasant one. So plus, what is it? 1/2 of 2y naught minus x naught minus z naught. 1/2 of 2y naught minus x naught minus z naught. 1/2 of 2y naught minus x naught minus z naught. There's probably a smarter way to write this, but this is the way I wrote it. So then that, of course, the top one, sine t, then cosine t, and then sine t. But the last sine t picks up a minus, which I'm going to implement over here. And there you go. That, my friends, is the integral curve to this vector field, hopefully through the point x naught, y naught, z naught. Now we can check my answer, right? What do we do? Plug it in. Times 0. If I put in t equal to 0 here, the top row, I get 1/2 x naught plus z naught plus 1/2 x naught minus z naught. And then this is 0. So the z naughts be canceling. 1/2 plus 1/2 is 1. The first component is x naught. That's a good sign. Yay. The next one, if I plug in times 0, I get x naught plus z naught plus 1/2 of 2y naught minus x naught minus z naught. So basically, this guy, right? Come on. This piece cancels with that piece and just leaves me that, which is y naught times 2 over 2, also known as y naught. Yay. So the middle component's y naught. And if we plug in times 0 into this one, and we work it out, we've got this minus that, which now the x naughts be canceling, and we've got z naught plus 1/2, so we get z naught. It works. So I have a question. Yep.
Is there a reason it's 2y minus x naught minus z naught?
Because that's what we found?
Oh, it was a negative. Okay.
Oh, okay. Yeah.
I got it.
I mean, all right, so I mean, this is the integral curve, and I mean, this is a somewhat challenging problem, I think, right? It would be more challenging if we couldn't just write down, right, the general solution from the notes, right? If you actually had to find that solution in addition to this, this would be, you know, more annoying. Now, if we actually had the matrix exponential, it's simpler, right? If you have the matrix exponential for a problem, right? We should notice this. Remark. If you have dr dt equals to AR with e to the ta, or as it was pointed out to me, the eta, if the eta is calculated already, then if you just put r of t equals to the eta times your, r naught, whatever that given thing is, that has r of 0 equals to r naught. See, because e to the 0 is 1, or the identity matrix here, right? So if you already had the matrix exponential on hand, you can circumvent this algebra we're doing on the general solution, right? Sometimes the algebra to fit the constants is pretty simple. Sometimes it's less simple. So as we go back and if you look at the row operations here, do I require you guys to learn row reduction in this class? No, certainly not. But I do require you to know how to solve systems of equations, even in the case that there's infinitely many solutions, because of course that's the eigenvector problem. So, you got to know how to do that. This thing I'm doing, row reduction, is it the best way to solve these? I don't know. I mean, I think if you just attack this directly, you probably can solve it easier, honestly. If I just attack this directly, I'd look at the first and the third equation, I'd add them, right? That immediately gives me that 2c1 is equal to x naught plus z naught. I've eliminated a variable, now we're at two equations, two unknowns, and you can solve it by multiplication by inverse. That would be quicker than this. But I wanted to at least show you row reduction just in case, you hadn't seen it. It is nevertheless a general method. All right, so let us move on. Although I do have one question before I do that. What if you wanted to find the Cartesian equation of the curve, the path in three dimensions? How would you do that? And does that question even make sense? Like, how do you describe a curve in 3 dimensions? How does that go? You ever think about this? Remember calculus 3, we parameterize a line, right? What's the equation of the line? That question doesn't make sense, does it? On the other hand, if I ask what are the equations of the line, well, that does make sense, because any line in 3 dimensions can be, it can be found as the intersection, right? Any line in 3 dimensions you can find as the intersection of 2 planes, right? You find 2 planes, it's the common solution of both plane equations. So to describe a curve in 3 dimensions, we need 2 equations. How do you think you could find those 2 equations for this problem? I mean, I think what I would do, I don't know what to do with that either. Look at that, guys. Whoa. I'll write it down. I don't know if I can solve it though, okay? I'm not sure we have talked, I'm not sure I know how to solve these kind of problems. Check it out. So dy dx, I think I would do, basically y dot over x dot. In other words, z over y, right? And if I was so bold as to do this, I would then do dz dy maybe. I probably should do dy dz, because then I can think about y as a function of x and z maybe. So that's, y dot over z dot, which would be z over, I don't know. So, yeah. So I think that my notation is misleading. I mean, what this really is partial y, partial x is equal to z over y, and partial y, partial z is equal to z over x minus y plus z. If you could solve this pair of partial differential equations, then I think that solution to that probably, see, I'm still missing something. It's not just that though, because, anyway, I'm actually just playing. So I really don't know the answer to this. I'm just speculating. So what I'm trying to tell you is that trick I did for 2 dimensions is a 2-dimensional trick. Whatever the 3-dimensional analog is, I'm not actually sure at the moment, to be frank. So anyway, I'll stop with that. So let us move on here. The next thing I want to talk to you guys about is like energy analysis and so forth. So if I can erase some things here. All right, so let us think about one-dimensional motion. In X, all right? And we'll assume a conservative force. So F is going to be equal to minus du dx, where U is, of course, the potential energy. So you guys know the deal. Mass times acceleration is equal to the force, right? But that's equal to minus du dx in our current context, right? But what more can we say? Acceleration is what? dv dt, right? And so we have m times dv dt is equal to, and this we could trade for minus d, oh, rats. Forgetting something, guys. Uh-oh. Yeah. Oh, I know what I'm doing. This is fine. This is not wrong. I just forgot my trick. So the trick is to multiply this equation by velocity. Multiply by velocity, and we get m times dx dt times dv dt, is equal to minus dx dt times du dx, right? But then the chain rule gives me that that's just minus ddt of u. All right? And on the flip side, this is m times v dv dt, which if you tilt your head and squint, you can see that that's the time derivative of 1/2 mv squared. So therefore, the derivative with respect to time of 1/2 mv squared plus u, right, is equal to 0. I'm not telling you anything you don't know, I hope. I'm telling you that if the net force is conservative, energy is conserved. And this quantity, of course, is the total mechanical energy, right? So it's a function of x and v, really, all right? E is a function of x and v.
Professor,
Oh, what'd I do?
where does the negative sign go?
Well, I rewrote it as on the same side, so
Oh,
yeah.
got it. Okay.
So look, so if we if we think about this as a system, you're like, wait, what do you mean system? This is a second order differential equation, right? So how do we make it into a system? Well, I'll tell you what we'll do is we'll think about simply x1 as equal to x, and we'll think about x2 being equal to, well, v, right? And so if we do that, of course we have x1 prime is equal to x2, right? As usual for the reduction of order, but x2 prime is equal to what? Acceleration, yeah, v prime, which is also like what? It's 1 over, well, it's minus 1 over m, right? Du dx. So let me put that all together. We've got x1, x2 prime is equal to, 0, 1, and oh, I'm sorry, I've gotten, what am I doing? No, this is not the thing to do. Strike that from the record. Oh, sorry, I had a math meeting earlier today. It has corrupted my thinking the whole day. Math meeting, you think, well, isn't a math meeting about math? No, it's not about math. Every math meeting, every time I have any kind of meeting about any kind of organizational aspect of the university, I lose a little bit more faith in the project of higher education.
Are we doing that well?
I mean, you guys are fine, but like the general organization of universities and the paperwork that's involved and the general reluctance to actually make anything about quality, it does wear on you after a while. Anyway, so listen, the point is, if we think about direction fields, we've talked about direction fields before a little bit. We can plot, right? Essentially think about the vector field, right? F, oh man, this is trash. Watch out. Yeah, that was close. So we think about F really of x comma v, right? And that vector field, we can picture it as, v comma minus 1 over m du dx, right? Which, of course, physically speaking, is v comma minus 1 over m times the force, right? Actually, skip the minus. It's just 1 over m times the force, right? So, in some sense, to understand this system is to find integral curves of this vector field in xv space. And what are the integral curves of this vector field in xv space? Well, they're energy levels, right? They're energy levels. So we can talk about something called a critical point. What's a critical point? What do we mean by critical point?
When you say your integral to 0.
When I set my integral to 0, well, a critical point here would be basically where the vector field is 0. And so for the vector field for this to have a critical point, where v is equal to 0 and where the force is 0, or in other words, where du dx is 0. Well, du dx being 0 is a critical point of the potential energy in the sense of calculus 1. So there's going to be a connection between the critical points of the potential energy and the critical points of this vector field. But anyway, I'm going to start this discussion over next class, and we'll spend like a full half hour on energy levels and such. I do have a surprise attack mission for you guys to take with you. And also a bonus point opportunity I will describe shortly, since you guys are here.